Hi, very good afternoon to all the students. How is everyone? Okay, so today we are going to have 1 hour class. I can see many of you have already joined in our class. Basically, I can see many of you. 29 minus 3 will be 26. There are still 5 who is going to come very soon. So basically today we are going to continue to discuss about the RAM. Before I start, let me see who is already in the class. I see that Chai Siu is already here. Chun Wei, Chong Yi, Han Xiang, Heng Dong, Jing Wen, Min, Ken Sing, Brenda, Koi, and then Leong Ho, Lok Jing, Mei Lin, Ernest, and also Tiong Le, and Bei Hong, Wen Liang, Xu Pian, Sherwin, Yan Chang, Yi Hang, Yi Si, Dong Chuan, Yu Yang, Zelin, and Zhang Hen. All of you have already been here. There are 26 of you. Before I start, any question you want to ask me? Any things you want to ask before we start our lectures today? Anyone? Yeah, I see one more joining. Yeah. A lot of people are here. The people list, show them all. Okay, sure. Okay, if you have no problems, then we will continue to study the RAM. For today, we will study how to design the RAM. So this is actually, basically this is the DRAM organization example. What is the DRAM? How actually the DRAM can be actually designed? Okay, so let me show you. Basically, this is the DRAM that you have for the computers. Yeah, so we have 2048, which is 2K, multiply 2K, multiply 4. In total, yeah, you can calculate how many in total, yeah? 2 multiply 2 becomes 4. 4 multiply 4 becomes 16. So 16 mega, yeah, over here. So for all the RAMs, you will need one very important component, which is the row decoder at the left-hand side. And then you will need a column decoder at your at the bottom. And then on top of this column decoder, there is a refresh circuitry. Okay, refresh circuitry. So these are all the connections from the row decoder, column decoder, refresh circuitry, and also the data input and the output here. So before you can come to this row decoder, you will have a multiplexer. And then we have the refresh counter so that you can refresh your DRAM. Then we have the column, row address buffer, and also column address buffer. So these are actually the organization of a DRAM. Okay, organization of a DRAM. So besides, we also have a lot of the control signals. So all these are actually the control signals. We have the row access signal, and then also we have the column access signal. We have the write enable, and also the write output enable. So these are all the very important components when you design a DRAM. So let us continue. So this is actually a typical 16 megabit DRAM. This is the 4 mega multiply 4. The meaning of this 4 later we will discuss. Yeah, so this is actually the 16 megabit DRAM. So if let's say the question asks you, you need to design a 16 megabit DRAM. So you design like this. So you must have the timing and control, and then you must have the refresh counter. Then we have the row address buffer, column address buffer. These are all the buffer. Then we have the row decoder and also the column decoder. On top of the column decoder, there is a refresh circuitry. And then we have the data input and output at the end. So why this is a 4? Because at the output, you will only, so you will get 4 lines. Later we'll see how to get the lines in the exercises. Okay. Yeah. Now let us go and study how do you actually connect the RAM together. A RAM is actually the random access memory. The random access memory, in short, what is the short form of the random access memory? Is RAM. So this RAM basically, it can be constructed using a few ICs. Okay, let's say we have the first IC. This is the first RAM. This is 16 multiply 4 bits, RAM 1, RAM 0. Then we have the 16 multiply 4 bit for the RAM 1. Okay, in case you have these two types of RAM, you want to connect, okay, 32 multiply 4 bits words memory can be constructed using two 16 4 bits chips. So you have two of these chips, chip number 1 and chip number 2. So this is how you connect. So basically, you need to have a inverter over here. Then we come here and then we connect to the chip enable. So this CS actually is the chip enable. You have to select which chip can be enabled for you to get the relevant output. Okay, so this is the one way. Besides, you can also connect in the other way. In this case, you can output all the 8 bits together. So here we have the 8 bit. But because you output at the 8 bit over here, so your address will only have 4 bits here. 1, 2, 3, 4, and then plus 1. Okay, here. You only have 4 bits over here. Yeah. So this is a difference between here and here. When you are given two ICs for the RAM, you can actually connect it to increase the address, become the 32 plus 4 bit, or you can connect it, become 16 bit multiply the 8 bit. So this is actually the way how you connect. Yeah. Okay. So any question before I continue? I think maybe I can let you to do a question first. I will launch a poll first. Let me launch a poll. Okay, which pins control and enable RAM chip? Okay. Okay, first option is CS. Okay. The second option is R stroke W A R slash W. And the third one will be output enable. The fourth one will be write enable. Which pin actually control and enable a RAM chip? Okay, I'm going to launch the pool now. Let's select, yeah. I will give you 2 minutes. Which pin actually control and enable a RAM chip? Which one? Okay, of course, there's controls and enables because there's only one pin, right? Can you start to answer? Okay, I can see many already start to answer, so very good. Okay, mostly has been answered correctly. which pins controls and enables a RAM chip. So why there is two lines of ABO? Two lines of AB0, AB0. Okay, there are two lines there because they want to control the two lines over there. Yeah, control the two lines. Okay, later I explain to you. Okay, now I'm going to end the pool in 5 seconds. 5, 4, 3, 2, 1. I'm going to show everyone the result and I end the pool. So this is actually the answer given by your friend. Okay. Let us see who did correctly. How many of you have done correctly? So which pin controls and enables a RAM chip? Sorry, there is a S here. Okay, now most of you select CS chip enable. Yeah, chip select. So it's very good. So let's give a big round of applause to all those who answer correctly. Very good. So regarding a question asking why there's two A not right, AB not right. Because this for this chip, basically you want to enable both of them together. Okay, A, B, not. So when we need to enable both of them together, so we have to have the AB, yeah, AB not here. When we want to enable this, you see this one is 8 bit. So this one is another extra signal. For example, you want to use these two together. So because you have 16 multiply 8 bit from the original 4 bit. So okay, you have to have the 8 bit. So basically this 0, 16 will be here, will be 0. Let's say okay, in order to represent this 16 bit, we just need from 0, 0, 0, 0 until 1, 1, 1, 1. So we have one extra bit over here. So this one, we just, we don't use it too often now. We just use it to do the chip select. Chip select over here. So when you have the, okay, it become the 8 bit over here. So we select which one we want to use. So let's say if this one have the 8 bit right over here, yeah, 0 to 7. So basically, we will turn on this or this, yeah, so that it become the 8 bit. Yeah. So this is a not over here. Yeah, 7, 0, 1. So this is what the meaning. Yeah. So basically, we want to use this bit. Basically, we select whether we want to enable the chip or don't want to enable the chip. Another one will be the chip select. So select both of them. Yeah. So this will be the way to do it. 2 to the power of 4. Okay. Don't worry. Just now who asked the question? I know who asked the question. Zhong Lei, yeah, okay. So when later when we do the exercise, then we will know more lah. Yeah. So yeah, this one, for example, let's say, yeah, okay. What's the question? Yeah, okay. So we will do some example later. So let me explain a little bit. For example, let's say this is the 4 bit. So for the 4 bit, the last address here will be used to select which chip to be used. For example, let's say this bit, okay, from the, you will select this one. Okay, so let's say originally you have a 0. Okay, originally you have the 0, 0, 0, 0. But because you have one more bit, so you can determine which one you want to use. Yeah. So you can actually come up with this one or from this one. Yeah. So this is an inverter. That's why when this one is 1, let's say, sorry, when this one is 0, so only the first chip will be enabled. And then this one come to here, 0 come to here, right? Then it will be enable. So this one enable. When it come to here, it become 1. Go through inverter, then this one will not be enabled. So at one time, only one chip will be enabled. Only this chip is enabled. So when your address is starting from 0, when AB4 equals to 0, okay? So only RAM number 0 can be used. Okay, when AB4 is equal to 1, only RAM 1 will be used. Okay, RAM 1 will be used. This is the idea behind. Okay, yeah. So let us go to the other one. Pyongle asked, yeah. Pyongle asked why we have the two AB. Actually, these two AB are the same. Okay, when AB, for this example, when AB equals to 0, what will happen? We have to go one by one. I go to here. This one will be enabled. Okay, so chips 1 will be enabled. When AB equals to 0, it's not connected to anything, other thing. So after that, the AB 0 go to this A, address A. And then this one go to the address A as well. So when AB equals to 1, what will happen? When AB equals to, AB 0 equals to 1, we first talk about the 0. So it's enabled. So what will happen? When AB not is 0, because it's active low, right? So it comes to here, then go to CS, so active low, because you see a bubble over here. So the RAM number 0 is enabled. When RAM number 0 is enabled, so you will see that all these output can be, these 4 bits, the most significant bits can have the signal when it's 0. Okay, so when it is 1, what will happen if it is a 1? In other case, when it is a 1, okay, if let's say this is the 1. If let's say it is a 1, this one will not be enabled. So what happens if this one is not enabled? So this all will become 0, 0, 0, 0. Yeah. So this is the meaning. Yeah. So that's why you can form the 8 bits. 8 bits from the 4 bits. Okay. So this AB not will be used to determine whether this first chip will be turned on or not turned on. Yeah. So when it's 0, then all of them will be with 0, then you will have the signal. If 1, then you will turn off all this. Yeah. Later we'll see this one. Yeah. Another question, yes. If AB let me see what is the question. If AB not, then you become, if AB not equals to 1, then you become 14 multiplied, 4 bit, no, it's still 8 bit, but the most significant bit will be 0. Yeah, most significant bit will be 0 because it's not enabled. Yeah. Later we will see because it's still 8 bit just that it's controlled by that one 0 there okay. So if 0 then is enabled, if not 0, if 1, let's say 001, then it won't be enabled. Yeah. So there's the basic but don't worry, later I will teach you more on this but this one is all about the signal enable, able or unable. Okay, so AB not over here. I think this is not easy this one because there are two here. Okay, AB not over chip enable always is enable together. Okay, CS and okay. So now let us go to do design work. We will go to the tutorial question. As promised, we are going to do some practice today. This is a very difficult topic. Yeah. So don't worry if you at first you cannot understand. Later you understand a lot. Okay, let us do the last question. Question number 4 of your tutorial 5. We are coming to the almost the last tutorial there. Yeah. Let me move this one above a bit. Okay, so this is the question. And let me also pull this one up so that we can see the whole question. At first, you might think that this is a very difficult question. So when we do together, then it won't be so difficult. We're all talking about the address. So the question is the memory of the computer system. Okay, the memory of a computer system is consists of 8K multiply 8 ROM. Okay, now we have the 8K multiply 8 ROM devices. This is 2, 8K multiply 8. Just now we have 2K multiply 4, right, like that, right? So now we have the 8K, and then got the 8 lines there, or 8 bit there, okay? ROM devices, and 2K multiply 8 RAM devices. The RAM is a little bit smaller. So these are the two computer memories exist inside a computer system. And then these devices are to access by the processor in memory address space at the location given in this table. So when the computer need to call ROM 1, they call from 000. Remember, this is a hexadecimal values to 1111. When you need to call the ROM number 2, you need to come from 2000 to 3FFF. Okay, and then when you need to access to RAM 1, you need to access to 8000 to 87FF. And then from 8800 to 8FFF, you can access to RAM number 2. Okay, now the very difficult question come in. What's the difficult question? You have to draw a circuit diagram. This is the most difficult thing, right? Draw a circuit diagram of the required address decoding circuitry showing the various connection between the address decoder, and also the 4 memory device, 2 RAM and also 2 ROM chip select inputs. Like what we did just now, we used the AB not to enable the circuit, and then the processor 16-bit address bus. Okay, now, since this is a hexa number, when we talk about this 1FFF, what is this? When we have the 1F, F, this is basically equals to 0001, 1111, 1111, 1111. Okay, still remember not? This is in hexa, Hexa means 16, base 16. Okay, so this is base 2, So now, when you have this, these are the address of the location of the ROM and the RAM. Now you need to draw a circuit diagram of the required address. Okay, so how do you draw? And then after that, you need to draw a table showing the contents of the address decoder. You need to know how to what is the content of the address decoder, and also what is the size of the address decoder. Explain your answer. So now, let me give you a few minutes to take to break this question and see whether you can answer or not. Okay. Hi everyone. Can everyone answer? Okay. Now I just now we discussed about this, right? A B node. Let us go very forward to this A B node. For this A B node might not be the same with this A B node, I think. Yeah. Because if let's say this one, later I will explain to you. Yeah. Because some of you might confuse about this, right? Don't worry, I will come back to this later. So, okay, let's see the answer. Answer about this one. Okay, question number 4. Don't worry, the answer will be given to you. So everything, all the answers were given to you. But this topic is a bit difficult. Okay, for ROM and ROM 1 and ROM 2. Okay, we have the ROM 1 and ROM 2. What is the size? The ROM 1 and ROM 2 actually have the size of ROM 1 and ROM 2 has the size of 8K multiplied 8. So this is the 8K multiplied 8. For this 8K multiplied 8, so we have the 8K multiplied 8 means the 8 at the end is actually the 8 data lines. In other words, this is the 8 bits. Okay, 8 bits. So we have the 8K multiplied 8 bits. So 8K, you need 2 to the power of 13 for the 8K. If you want to represent 8K addresses, you need 2 to the power of 13. So you have 13 address lines. In order to represent 13 address line, you need 13 bits from A0 to A12. So now we go to the RAM. For RAM, it's a little bit different. It's a 2K multiplied 8 bits. 8 bits RAM. So 2K, you need 11 address lines. 11 address lines. So when we come to this address, we have the 0000. There are 16 bits over here. Okay. So when we come to 1FFF, also got 16 bits because there are 4 hexa numbers here. So let us go to the answer. The answer here, when we see the address of the ROM number 1 over here, so it's from the 000 to 1FFF. So if you convert this 0000 to hexa to the binary number, what is the number you get? You get 0 becomes 0000, right? 0 becomes 0000, and 0 becomes 0000, and etc. When the 1, you have to convert it become 10001, and the F become 1111. But F is actually 15, and the F is 1111, and then this F also 1111. So just now we talked about ROM consists of 13 address lines. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. All this from here to here, from the 13, from the 1 here until why I cannot select. Okay, until the 1 over here, until this 1. Yeah. So these all are actually the address that we want to select, right? These are the address. Because you only need 13 address to represent the 8K. So now, leftover is 3 bits over here, 0, 0, 0. Okay, this is for first case. For the second one, ROM number 2, because you also need 13 bit, so that's fine. Let me use this one because I cannot draw here. I try to contain a little bit. So now you also have the 13 bit over here. So what we can see here is that because we have the 13 bit, so anything come after this 1 and 1 here, the last 3 bits are actually the control signal, and these 13 bits are actually the address of the ROM. Because it never use everything. So remember, this 0, 0, 0 is the control signal, and then this one is the address signal. However, for the RAM actually has an 11 address line because it only has the 2K, 11 address. So anything here from here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 11. Okay, anything after this one, anything after this one will become the control signal. Okay, anything come from here is actually the address. So for this case, it's different. Here to here is actually the address. Here to here is actually the control signal. So when we have this kind of data, so how do you actually design the whole address so that you can map to all these 4 memories? So we have to see the difference in the address. So the difference in the address here is that 1 is over here and 0 is over here. So how do we name this whole bit? The bit sequence, how do we name it? Let us study how do we name it. This one we call it A0. Okay. Later, one by one, after we have learned all the names, then we are very good already. Okay, now we have the A2 over here and A3. Yeah, then A4 and A5, A6, A7 over here. Okay, I'm not going to name everything. If not, then it's waste a lot of time. A8, A9, A10, A11. Yeah, A11, and then A12, A13, and then A14 and A15. So these are all the name of each of the bits. You do see it's just 1 and 0 actually for the name, very special name for each of them. Yeah, because why? Because if you don't know the name, then you cannot do. So you can observe that for the ROM, you can observe that all of them, all the control signal are actually the same, except which one? A13 for ROM. A13 is different. In this case, if you can use the A13, you can actually differentiate between the ROM 1 and ROM 2. Okay, you can differentiate. You want to enable the chip or not? Let's say you have the ROM over here, ROM 1 and 2, ROM 1 and ROM 2. Let's say you have a chip select over here, chip select bar, and then chip select bar over here. So if you have the A13 signal, you connect to this chip enable bar and also the chip enable bar over here. Okay, you can differentiate which one you want to enable, right? If it is a 1, you want it to enable ROM 2, right? If 1, then enable the ROM 2. So if not 1, then you have to enable the other one. So which one you have to have the inverter? If 1, you want to enable the ROM number 2. Okay, so if 1, it becomes 0, right? So you have to put a inverter. If 1 over here becomes 0, 0 enable. Yeah. So if 1 over here, so this one become 1, so this is disabled because this is called the active load. Yeah, I think you learned this in your digital electronics. So the 13-bit is very important here. The other thing very important is we want to separate between this and this. So if let's say you see a 1 over here, definitely it is a RAM, right? You see a 1, it's a RAM, right? Because ROM does not have a 1 here. So 1 over here, so it's a RAM. But if you want to know which RAM, when we talk about RAM, yeah, you can know, but it depends on this A11. So A11 will determine which, this one A11 will determine which RAM. Determine which RAM, okay, which RAM. Yeah, so that's why this is the addressing. When you do this, then you will be able to come up with a table. This is a table. How do you actually differentiate between ROM 1, ROM 2, RAM 1 and RAM 2? How do you differentiate? So from 0 means if you have the 0 over here. Let me use a whiteboard again, because I need to translate a little bit so that we all know how to do it. Yeah, although you see only 0 and 1 actually very complex. When we see 0, what have we seen? That we have the 0 over here. So which means it is a ROM, right? It's a ROM. When we see the 1, for the A15, it's a RAM. But how do you differentiate between ROM 1 and ROM 2? It differentiates by A11. Whereas for the this one A11, 0, 1. If let's say sorry, A13, sorry, A13, not A11. You can select the A13. Okay, now you see, when you have the A13 0, you will select the ROM 1. Okay, if you have the A13 as a 1, so what you select? ROM 2. And then for the RAM also same, but the RAM that does not rely on this, does not rely on A13. As you can see, the of the address is actually rely on this one. So the 0, so it will enable this RAM 1. And then for 1, it will enable the RAM number 2. What if A13 is 1? Then nothing will be enabled because it's not the RAM 1 or RAM 2. Yeah, that's the meaning. Okay, now we go to the answer, yeah? Because if without the answer, you cannot see. So this will be the circuit diagram that you can see. Yeah, let me show you this circuit diagram. Let me also do the pane, the whiteboard. Full screen. So how do we draw the circuit diagram to represent, to design the RAM and ROM combination? Okay, this is actually the circuit diagram. So you might not be able to see clearly, but don't worry, I will label it for you. This is A15, A14, A13, A12, A11, A10. Okay, and then this is A0, and of course, there are at least 11 bit over here. So you can see that for the ROM number 1, this ROM number 1, this is a chip enable, yeah, enable chip. So for the ROM number 1, it can only okay, it will go through this one, address decoder over here, the address decoder, the ROM decoder over here. So it will come here. If let's say this one going to the A11, A13, and A15. So this is A15, okay, A13, A11. So you code according to the table that we have discussed just now. If let's say you have those number, then you will enable the A. So enable the A if the code is right. Okay, so it will all go to there are 4 lines over here. So you will go and enable this one. You put a 0, then it will be enabled. Then you will take the data from here. If let's say B is enabled, so you have the 0 here. So this one will be 0, then this one will be active. Only one of them will be active at one moment. So this will be the design. Any question? Let's ask. I know this is a very difficult topic. Let me see who has a question. Any question? This will be actually the design of the whole. So A14 carry no meaning. Let me see. I don't dare to say so. Let me see the A14. We go and see the. It's a very good question. Yeah, correct. Very good. Yeah, A14, is it carry something to see? Yeah, nothing, right? No, A14 and A12 also is not used. Okay, it's not carry anything, any meaning, yeah. It's not meaning. What is the purpose of this A14 and A12? Yeah, a very good question from this Xiaoping. Yeah, this for the A12 is the address for the ROM. Yeah, you're right, correct. How about A14? Yeah, A12 is address for ROM, very good. Yeah, Jonathan said, Jonathan is very clear about this. Okay, A12 is the address for the ROM. Yeah, correct. How about A14? Let's say you have a 16-bit computer. Any purpose? A14, nothing. At this moment, yes, nothing, but in case you need to add on other RAMs. For example, you want to expand your computer to add on another 2 RAMs, then this will be useful. This for future expansion. Of course, they will use up everything, right? They haven't used to the maximum address. So this will be the design of using the main memory address. So let's say you have a 16-bit computer. This is the maximum you can get. 16-bit means you can have 64 kilo address. That's why, I'm sorry, 64 kilo address. Just 16 bit, right? 64 kilo address. But let's say if you have 32 bit, you will be very large already. Yeah, because how many? 2 to the power of 32 bit, 4 gig already. 4 gig address. Last time it was it was a lot, right? 4 gig. Now some computer got 8 gig memory, right? So it become not enough already, right? So they move to 64 bit. Yeah, that's the reason why 64 bit now is very useful, very enough, right? It's enough. Then yeah, very enough. So now this will be the answer. So I'm going to post this answer to you. Yeah. So yeah, Junghun very sharp. A12 is for the address for the ROM. Yeah. Now I'm going to post because I know all of you are very eager to get the answer right for tutorial 5 solution. I'm going to post to you so that you can just study first. And after that, you can ask me if you have any question. I will post this to you. Yeah, this is a very difficult question, but you will learn a lot, then you will know how to do it. Me, where is my folder? Okay, so we go to solution 5. So I'm going to post this answer to you. So hope you can actually read beforehand. And next time when we do other tutorial question, then you already understand this. This is not very difficult, but because it involves the digital, so you must be very good in all the binary numbers, hexadecimal numbers, etc. So you can have a look. So the answers will be like this. First, you find out what are the address lines required. Then you represent them using different address line. Yeah, using different address. After that, only then you control which one will be used to control which one. In this case, you can see that from this table, 110 and 111 has not been used. So you can actually add two more things over here. Yeah. Then there is a redundant one, right? Is it redundant? If 0, 1, this one also represent this. This one also represent this. Is it redundant? If redundant, then you can use it later. Yeah. So yeah, for this one, everyone can go back and think why AB naught is over here. Yeah, AB naught is over here. It's the 8-bit one, 8-bit. So AB naught over here. Yeah. So next time I will explain on this. Don't worry. This I think this has this design has their own reason. Let me study a little bit. But in me, I will put AB3. Yeah. But never mind. It's the same, just that it can represent 8 numbers when you enable. So when this one enable, then you can get the 4-bit over here. Yeah, 0, then you can get the 4-bit over here. Yeah. So depends how they want to name it. And then if it is because I think if this one is AB3, it's easier to use. AB0 will be harder to use. Later they will have to program it differently. Yeah, but it's still working. It's still working. Yeah. Any more question before we end the class? Because it's already 3:21. Anything you want to ask? Yeah. Anything you want to ask me? Let me ask one of you. I'm not going to ask everyone already. Let's. Chai Siu, any problem? Any problem, Chai Siu? Any question you have? No question. Okay, very good. So study the tutorial. Yeah. Boon Kyung, any question you have? I haven't asked Boon Kyung. No. Chie, are you okay? Yeah, mostly after this, mostly we will learn about the theory of all the storage device because tutorial I think 5 only. So, but this tutorial part is very important. You need to know how to design. Yeah, it's very important. So, if no question, then thank you very much, and you may leave the class now. Thank you, and see you. See you next week, and enjoy your holidays and happy Chapter. Okay, thank you. Okay, bye. Okay.